Okay, so my name is Carl Steinbach. I'm the tech lead for the Hadoop platform team at LinkedIn. And today we're here to talk about Dr. Elephant. I'm just going to give a quick sort of like introduction and a little bit about the motivations for building this, and then Fangxi is going to jump into the technical details. So I think to sort of properly understand Dr. Elephant, you have to understand where Hadoop came from at LinkedIn and where it's at now, and the problems that created for us. So LinkedIn was a pretty early adopter of Hadoop back in 2008. Some engineers heard about it and started using it. And the first cluster had 20 nodes. There were only 10 users, basically limited to one group, which was working on a product at that time called People You May Know, which is the sort of like fundamental triangle closing app, which allows us to recommend new users and was really an engine of LinkedIn's growth, especially in the early days. So back then, 2008, we had 10 users, 10 production clusters, and the applications that people were using were pretty much limited to MapReduce and Pig. So like all good things, gets more popular over time, and that brings us to now. So running through the numbers, we've gone from one cluster to over 10 clusters, a handful of users to more than 1,000 users. More than 10,000 nodes. And I think probably some of the more significant factors have to do with really the diversity of the things that people are doing on the clusters. So we went from sort of two supported engines or analytic environments to a wide variety, and the open source ecosystem keeps producing new and interesting tools, and engineers at LinkedIn keep implementing new, better tools. So it's a constant sort of struggle to keep up with all of this. So we learned some things along the way. We're getting to the point where we've been doing this for 10 years now. And I think the one big observation is that building big clusters is a challenge. If you read blog posts about Hadoop or books, all you're going to hear about is the multi-thousand node clusters, because no one wants to talk about the median cluster size, which is really something more like 10 nodes. So most of the vendors, if you look at their customer base, it's people running fairly small clusters. And when you go from, let's say, 500 nodes to 2,000 nodes, there's a pretty big difference in terms of the problems that you run into and the issues that you deal with. But I think somewhat surprisingly, we learned that while the solution to some of the scaling issues in terms of hardware is usually a challenge, but you can sort of press ahead with it and get there, scaling user productivity, especially when you have more than 1,000 users, when you don't place restrictions on the types of applications that people are allowed to run in the cluster or the types of problems they're allowed to solve, that's actually a much bigger problem. And it also turns out we discovered that these two issues are actually kind of tied to each other. Because a lot of these tools that exist right now allow you to get an answer to your question, but unless you invest a lot of time in tuning the way that you ask that question, the amount of work that application can trigger on the cluster may be really large or really wasteful. While with effort, a lot of users are able to figure out, like, how do I express my question in Pig or Hive or MapReduce for that matter, asking them to then spend sometimes just as much time figuring out how to tune that job to get that answer efficiently is something that users at that point don't want to deal with. And another problem is that even if you tune it, let's say on Monday, by Friday the job could be out of tune. So it's also sort of a constant tax, a maintenance burden placed on users. So the relation, of course, is that there's a trade-off. I mean, you can either ask people to spend time every week or every month retuning their jobs, besides which learning to tune the job in the first place, and that's a cost. Or you can just let them run untuned jobs on the cluster and then have to build bigger clusters. Dr. Elephant really is, the goal is to find an ideal solution to this where we provide a tool that helps users to tune their jobs for them. So we're able to get efficient jobs that make the most of the hardware resources that we're providing, while at the same time not squandering the hours of developers and data scientists and analysts. So at this point, I'm going to hand the mic over to Fangxi, who's going to give an in-depth look at Dr. Elephant and how it's built. Okay.
Ooh. Okay. Okay, so I'm going to talk about .elephant. I'll start with a brief introduction about .elephant, its motivation and history, and then I will going to give an overview of the service and its architecture, and then I will going to do a quick demo about it, and we will talk about some of the service we built on top of .elephant, and how we use .elephant to help us at LinkedIn. And finally, I will talk about some open source status and the roadmaps for the .elephant. Yeah, so I will start with the motivation. The first thing is efficiency really matters. So each individual job or individual workflow is very important to the overall cluster utilization. So if each job in the cluster save 10% in terms of memory or CPU, essentially you save 10% of your cluster. And the second thing is people have different levels of Hadoop skills. So some people are hired as a Hadoop master, but most people doesn't have those Hadoop master skills. So Hadoop has thousands of parameters that you can tune for your jobs, and most people don't know about that too much. And some people don't even know that they are writing Hadoop jobs that may have some problems for the cluster. So that's a pain point for us as well. And third thing is we find people are making common mistakes that can be solved by similar tuning tips. So people will come to us, we as a Hadoop team member, we provide some user support. People will come to us asking for tips to tune their jobs. And we find that we are constantly giving the same tips for every user. For example, split size. So your job may have some small file problems, and so we suggest the user to probably bump the split size and let each task, each mapper processing more data. Or for example, the parallelism, but by default, Hive may not use a lot of reducers. And if you do a very big drawing, your job may run forever. And in this case, we probably suggest the user to bump the parallelism and increase the number of reducers so that your job can run faster. Yeah, so I will keep talking about that. So here I talk about a few pain points we have before we have .elephant. And given those cases, we feel that we should build a tool that we can automate the tuning for every job. And in a user's perspective, we provide a service that they can use the service to get the performance diagnostic about their workflows, so that they can tune it automatically without coming to us and ask us to help them tune it. So we built .elephant. And what is .elephant? .elephant is an automated job performance monitoring and tuning tool for Hadoop. Initially, we only support MapReduce jobs, and later we added support for Spark as well. It is a single host, single process web app that can run on any host within a cluster, as long as your cluster as long as the host has access to job history server or HDFS. And it is job-based, which means that it analyzes the MapReduce job or Spark job right after it finishes. So usually, when your job finishes within 1 minute, you should be able to see your job performance report from the .elephant's UI. And we use .elephant use a rule-based configurable heuristics, which means that we can predefine a set of rules that will go against each job. And it is configurable if, so the rules we use at LinkedIn to analyze a job may not be suitable for other companies. In this case, you can extend build your own heuristic. We provide a set of interface that you can just write some code and to build your own heuristics. So it is very flexible. And at LinkedIn, .elephant right now analyzed 100K jobs per day. It runs on all of our clusters. And we have hundreds of daily users that use it to tune their workflows. So this is the architecture about .elephant. So as I said, .heaven is a single process app. So here, each orange rectangle here is the thread inside .heaven. And we will start with the top level. We have a job generator that for every 1 minute, it will fetch a REST call to the resource manager and get a list of jobs that finishes within the last 1 minute. So here, each rectangle, each triangle here is a MapReduce job, and each octagon here is Spark job. So in our case, the job generator gets 3 MapReduce jobs and 2 Spark jobs. So we will use MapReduce job as an example. So the job generator will pass the MapReduce job to the MapReduce fetcher. In this case, each job here is just simply the ID. And the MapReduce fetcher will fetch multiple REST calls to the job history server and get a detailed data for that job. For example, it will get the job metadata, its queue, its job name, or start time, end time, and job configurations. It will also get counters or time for each task. So after the MapReduce fetcher get all the required information for this job from job history server, I will pass this job to the MapReduce analyzer, and we have a set of rules configured inside this analyzer. I will go against the job. So in our case, we have 3 rules configured for the MapReduce job. We have rule 1, rule 2, and rule 3. And for this job we analyzed, it gets a green score for rule 1, and it will get a green score for rule 2, but it will get a red score for rule 3. So when we give a green score, we mean that this job is good. In .heaven's perspective, this job is good. It doesn't need any tuning. But if it get a red score, it means that it has some serious problem and it should do some level of tuning. And in this case, this job, since it get a red score, so .heaven will assign a red to the job and will save the result in the MySQL database. So this is the backend of .heaven. In the front end, a user can get a list of, see a list of jobs that .heaven recently analyzed, and the user can search for the job they concern by job ID or workflow ID. So this is how the user at LinkedIn use .heaven. They just search for the they just search for their workflow ID and get a list of jobs in their workflow. So I will do some quick demos about .heaven. So this is this UI page, and for each job here is you can see we have a list of rules, and each rule has a result for this job. And for this job, we can see that it has a red score for the mapper memory rule, and it has a orange score for the reducer memory rule. So since it has a red, this job will get a red score, which means that this job needs some tuning, especially in its memory settings. So if you click on the job, you will go to the detailed page that we will tell you why we give this job for example, a orange score. And then we will also provide some helper pages that user can use to tune their job. So here, if the user click explain, it will redirect to a helper page that user know how to change the job parameters to make this job run in a better way. Yeah. So this is the detailed analysis result for one particular MapReduce job. From here, this is all the mapper-related heuristic, and we can see we have a data skill heuristic, which we test if this MapReduce job has some data skill problem, and we have a GC heuristic, which we test if the mapper in this job uses too much GC time. And we have a time-related heuristic. We will see if the MapReduce job run, the mapper for this MapReduce job run in a reasonable time range. And we have a memory heuristic. We will see if the mapper uses reasonable memories. And we have a spill heuristic. I will test if to see if this MapReduce job spills too much data on disk. And I will choose the time-related heuristics for detailed demo. So this is like 3 analyzed results for 3 MapReduce jobs. And this MapReduce job get a green score in its mapper time because like this job, the mapper for this job has the average 10 minutes. So which means that we feel, okay, this is the ideal time that we want the job to be. So we give them a green score. And for this MapReduce job, like it has 100 tasks, but it has 100 mappers, and each mapper runs more than 2 hours. And in this case, we feel you should probably tune your MapReduce job, and because like if the job the mapper runs too long, it's bad for the overall cluster scheduling. So we feel in this case you should like tune this job and use more mappers, and each runs less time. And this is another example. In this case, this mapper runs. This job has 1,200 mappers, and each mapper on average run only 20 seconds. So this is also bad because essentially you are wasting a lot of resources. So in this case, we'll also assign this job a red score, and we will suggest the user to decrease the number of tasks. Probably like 100 mappers should be enough. So in this case, actually, we can save a lot of resource because for each task, it has some time to it wastes scheduling resources, and it has some task setup and initialization time. Yeah, so and if the user, so we provide a very simple way. We use a configuration file that user can configure the cutoffs for the heuristics. But if the user are not satisfied with that, so they can also extend the interface and build their own heuristics. For other companies, their understanding of mapper time may be different from us. So in this case, you can just feel free to write their own heuristics. Yeah. So another feature about .heaven is we want to understand why the job or workflow performance is changing over time. So as the data size is growing, like the performance of the job or workflow is also changing. So in our case, so since .heaven analyzes every job and save the result in its database, so essentially we have a history of the performance of each job or workflow. So in this case, we can display them and let the user see the trend of their flow jobs or workflows. For example, when you are developing a flow, you can compare for each time you make some code change, you can have a new run of your workflow, and you can go to the .heaven and see the workflow performance change between each runs. In this case, you know if you make a better change or not. Or like for example, usually your job runs 5 hours, but today your job or workflow runs 10 hours. You want to know why, which job caused the problem. You can go to .heaven and see it as well. Or we can even provide you some alerting feature. It means that you can, we can draw a plot for you, and you can see how your performance is changing over time. So you can even predict that some problem will happen soon. So this is one of the feature, the graph we draw, and right now we also support some other graph as well. So in this case, like each row here is a run of the workflow, and you can see essentially you can see a history of your flow runs. And finally, I'm going to talk about the service that we built on top of .heaven. I think I don't have time to talk about the motivation, but I will just demo the feature. So basically, we built a Jira bot that provides an automated service for user to tune their jobs. So if the user wants, at LinkedIn, if the user wants their workflow to run in production, we enforce a process that we will let .heaven to approve the user and letting the user to run their workflow in production. So what we do is we build a Jira bot. We build a automated Jira bot that run on top of the Jira. So a user can file a Jira ticket, and the user can call .heaven. Basically, it can add .heaven to review their workflow. So if .heaven find the user, call him, he will get the workflow ID from the Jira ticket field, and we will fetch REST calls to the real .heaven service and get a list of the performance analytics report for this workflow, and we'll paste the result on just comment it on the Jira. So if the user comment to .heaven, say, .heaven, please review my workflow, and .heaven will come automatically several minutes later and paste the result. So in this case, if the user can use .heaven to automatically review their workflow, and if everything is good, if everything is green, and .heaven will provide grant the user the privilege to run the workflow in production. This is how we use .heaven at LinkedIn. So yes, when we just released the service, we have a few users asking us if .heaven is a real person. But actually, yeah, actually it is Jira bot. This is a fake account. It's yeah, and we also have other services we build on top of .heaven. For example, a daily report. So every day, .heaven will report or alert jobs or workflows running on our clusters with the worst performance. So .heaven will send a private email to these users, letting them tune their jobs. So this is the user will feel, some users say they feel ashamed by it because they are caught by .heaven. And if and .heaven will also monitor the workflow performance, even if they has been running on production. We find, okay, so in production this job has some performance degradation. .heaven will force the user to do production review again. Basically, they need to tune their workflow again before they can run on production. And we also have some cost to serve analysis service. So the data saved in .heaven database is used to analyze the cluster utilization or resource consumption. Especially, we did it with separated by organization, so we know which organization used most of the resources within our cluster. Yeah. Okay. So. Finally, I will talk about some .heaven open source status. So we open sourced .heaven in April 2000 this year, and since then we have more than 10 people contributed to .heaven, and we have more than 40 commits, and we have more than 50 topics in our user groups. And there are a lot of companies contributed patches to .heaven, including Airbnb. We know Airbnb has been running .heaven in production, and this summer they hired a full-time intern and focused on improving .heaven, and they help us extending .heaven to understand more about their Airflow scheduler. And we have Foursquare, Everstring. This is a Chinese big data company, and they help us translate all our documentation in Chinese. And we have PayPal, and so PayPal also has been running .heaven in all of their production clusters. And we have some other company as well. So the last slide is the roadmap for .heaven. This is the work that we are currently doing to improve .heaven. The first thing is beyond MapReduce level analytics. So right now, .heaven focuses more on the MapReduce job, and we want .hyphen to understand more about the higher level knowledge, like peak hive cascading. So it can provide some tuning tips in the in their framework level. And we want to support the other schedulers like Woozy and Airflow. We have a basic support for Woozy, and the Airflow is contributed by Airbnb. And right now there is an active thread discussing they want. Right now we support MapReduce and Spark, and they want to support the TES as well. And another thing we are working on this quarter is we want doing something beyond the batch analytics. So right now, .hyphen analyzes a job right after it finishes. So we want to provide some real-time insight in while the job is running. This is maybe particularly useful for some long-running applications like Spark streaming. Also, we are thinking about like adding more analytics to failed jobs. So for example, so right now, like if the job fails, we display its stack trace, but we don't have more analytics on those stack traces. But actually, we feel the stack trace can be very useful because there are a lot of stack traces can be aggregated together and to provide some similar solutions for similar stack traces. So we use some. We have a project called exception fingerprinting, which essentially trying to get a fingerprint for each exceptions, and we want to aggregate the similar exception together. And in the future, if we see the similar exception again, we can provide some tuning tips for them, or in this case, it's the solution, some common solution. So if the user run some Hadoop job and fail with some exception, they can instantly get a solution from us. And finally, is some low-level JVM level analytics. So basically, we try to get some task profiling data, JVM profiling data, and we provide some deeper knowledge about that as well. Okay, so this is what's currently going on for .hyphen. And if you are interested in like knowing more about .hyphen, we have some resources here. We have our GitHub page. We can just search for .hyphen. That's the first thing come out will be the .hyphen on GitHub. And we have a Google user group that people can post questions. We have some full-time team member working on .hyphen that will respond very soon. And we also have a blog post that give a introduction about .hyphen. And we also have a presentation in Hadoop Summit 2015. You can find it on YouTube. Yes, so that's what I'm going to present today, and we can go with some questions. Yeah, so it's a Q&A time. Sure.
So basically, once you see that the job needs to be reviewed, I mean the system doesn't give any hint to the user what needs to be done. The user needs to go and figure it out.
So by default, like for each job, when it finishes, we will save it, analyze and save it in the database, so user can search for their job or search for their workflow and get a list of jobs they are interested in to tune. And also, if the user want their workflow in production, they have to tune their jobs. So you use the Jira service then to force the user to tune their jobs. Yes.
So the UI basically gives instructions for the changes that a user needs to make to their job. So I would, in some ways, describe Dr. Elephant as like a performance tuning wizard, but wizard has a pretty bad name in the software community, so maybe it's more of a doctor, right? And just like a doctor, I mean, they can give you a treatment regimen, but if you don't take your pills, it doesn't do any good. So that's that.
Go ahead.
So how do you get the actual data from logs somewhere? Or
Yeah, for MapReduce job, we get it from job history server.
do you have to modify the cluster in any way or configure it?
No. So job history server is both a set of REST APIs.
The job history.
Yes. For Spark jobs, we parse the Spark logs because at that time Spark's job history server doesn't give a good REST service. Yeah.
There's also a lot of work that's been happening upstream on something called the application timeline server for Yarn, and that work has gotten to a state where it's, I think, kind of production quality, and we're very interested in integrating Dr. Elephant with the ATS, since that looks like it's moving in the direction of being sort of the standard metric store for it.
What other kinds of rules do you have, and can you give a few examples?
Yeah, I think I have a slide that give a list of rules we have. So, yeah, let's see. Yeah, so this is our predefined rule for mappers. We have like almost the same for reducer as well. For mapper, we have a data scale, we have GC, we have time, we have memory and speed. So yeah, so this is has been tested and improved based on the user feedback at LinkedIn. So I think this has been well tested. Yeah, so when we develop these rules, we develop them based on our experience. We feel that we should make this user should try to improve based on yeah. So essentially, this is based on our previous tuning experience, and we will modify and improve the heuristics based on the user feedback later.
So there's a plugin API for defining these rules. And the API allows each rule to basically select the metrics that it's interested in, and then it also allows the rule to configure how it wants to display the information. Probably in this case, actually, we're showing a little bit too much information to the user. I mean, they don't need to know the precise value of any of these numbers. They mainly need to know that their job is sick, and here's what they need to do to make it healthy again. And probably the other main thing is telling the user, this is how much you're wasting every day or every week, that you don't have to. Another thing also that most rules allow you to do is to actually configure sort of parameters for the rule. So you can set the cutoff point that defines where a job goes from being sort of under the weather to being, terminal. Since it is a plugin API, we've seen other teams at LinkedIn, as well as people outside of LinkedIn, actively developing new rule types. Next question in the back. Right, so one of the big motivations for us to build Dr. Elephant was this process that had been instituted, I think, back in 2009 when Hadoop really started to take off at LinkedIn. And the people who were running Hadoop at the time, to their credit, realized that if we just let people onboard to the system and write whatever they want, it doesn't matter how many machines we throw at this cluster, it's always going to be super slow. And since also at that time, there was no real solution to isolate one job from another job on a cluster, we had to figure out a way to make sure that the jobs that were mission critical, that had tight SLAs, that they actually finished on time. So we did what I think a lot of companies have done, which is you have a development cluster and a production cluster. We then had to institute a process for how do you get promoted from development to production. And the process that was put in place involved the job owner basically filling out a questionnaire and then adding their name to a waiting list, and maybe a month later you would get contacted by someone from my team who would then say, okay, we're gonna have a face-to-face meeting for an hour, and they would tell you what's wrong, and then invite you to reschedule for yet another meeting after you had made those changes. And all the while, your job is running on the development cluster. Only once you get the seal of approval do you promote it to the production cluster. The really embarrassing thing about this process was that nothing prevented users from then continuing to modify their job once it hit production, and we saw that all the time. So whenever a completely stable job missed an SLA, or it caused other jobs to miss SLAs or stuff like that, that was always the first question, who changed something when they weren't supposed to? And the other sad fact about it is that at these production review meetings, clearly I could have sent a robot to them, to sort of answer these questions. It was all very mechanical. So Dr. Elephant is our approach to automating as much of that process as possible. So instead of filling out a questionnaire, Dr. Elephant collects a lot of these statistics for you. If you want a review, you just create a JIRA ticket, and we have this agent process that runs and looks at JIRA tickets, goes and looks at the job itself, and then we'll sort of broadcast a health report on the JIRA ticket. And then the JIRA gives us a way of actually tracking a paper trail of the promotion process from development over to production. And finally, it allows us also to monitor jobs once they hit production, because rather than locking it down to the point where people can't make any changes, we feel it's better to allow them to make changes but catch mistakes early on. Cool. Any other questions? Yes? Stack analysis. So you're not talking about exception stack analysis, you're talking about like okay. Right. So there's something something that's related to Dr. Elephant in the sense that it's another thing that we've invested time in to improve user productivity, and that's a tool called Bytecode, which is kind of like an X-ray, goggle system for bytecode. One of the problems with Azkaban, one of the things that we don't like so much, even though the rest of the system is really cool, is the fact that it allows users to upload zip files containing bags of garbage, basically. And you have a lot of people using the system who are not Java programmers. That's not what their job calls for, right? They're data scientists. They're trying to make sense of data. Class path hygiene is hard enough even for professional Java developers, but when you have a situation where people are like sharing jar files with each other and stuff like that, you can run into some pretty gnarly class path conflicts. So Bytecode will scan the contents of a jar file at the bytecode level, and it will find class file conflicts. When we migrated from Hadoop 1 to Hadoop 2, we were confronted by the fact that even though the APIs in Hadoop 1 or in Hadoop 2 are source compatible with Hadoop 1, they weren't binary compatible. So it was this weird situation of having to say, well, we need you to go and recompile your job and then re-upload it, but you don't need to change any of the code. So at that point, we actually sent a Bytecode to modify bytecode. So as a user uploaded their job, it would go in and look for these specific cases where, for example, a class had changed to an interface, and it would add a little bit of additional bytecode to cover up that problem. And probably took someone on my team maybe a couple of days to do that, and it probably saved a couple months of aggregate developer time in terms of the migration. So seems like a good investment to make. So that's some sort of stack analysis we do. Another thing that we've started working on is being able to predict that a job is going to fail on the cluster because of a class not found exception. And we see a lot of cases of people wasting a lot of time when they keep uploading a job, running it, and it fails. And this is a problem that you should be able to catch with static analysis, or at least warn people of. And then another thing that we do is, with Bytecode, we scan to make sure that people aren't, let's say, inheriting a transitive dependency from Hadoop, which may change when we upgrade Hadoop, and then their workflow would fail as a result, so we're able to warn people about that as well. Any other questions? Yes? So we've started working on that, and we have some, in fact, I think Fangxi could probably describe.
Yes, so the alerting feature is one of the things that we're actually working on .heaven. So basically, what we're planning to do is we want to give the user the ability to subscribe to a particular job or workflow. So if like someday it gets some anomalies, or the user can get alerted. Yeah.
Yeah, so we are looking into adding those features. I think one sort of like challenge that we're faced with is that Dr. Elephant is in the advice business, and as soon as people stop finding your advice useful, they stop reading your email, They stop answering your calls and stuff like that. So, and we know that we sort of can only like lose the confidence of users once, and then it's pretty much gone. So we're being really careful to make sure that we're not offering too much advice or not offering bad advice. But definitely tracking how performance changes over time is one of the things that we're super interested in. Also tracking how things in general on the cluster change over time, because typically when something breaks, my first question is always what changed. And when you're talking about a multi-thousand node cluster with more than 1,000 users, a lot can change. So being able to quickly narrow that down, to the set of changes that may have some relationship to your problem is a big concern for us.
So I think currently in .Hyphen, if you if I have one job, you can actually see a list of the historical performance for the same job runs. So if you click any job, you can see, and there's a link inside .Hyphen that you can use to see the historical runs for this job. So this is the current status. But I think right now we are working on providing more insight for that. Including letting user to actively subscribe, and we will alert the user for significant job performance changes in the future. Yeah.
What I wanted to add really quickly, what I was saying before, is that we want to give users the ability to sort of set knobs in terms of when to alert me, because we know that that's not going to be the same for every user. And some people, if they're working on something that's like super high priority, needs to get deployed the next week, even if it is inefficient, and then they're going to come and clean it up later. We want people to have the ability to temporarily turn these warnings off. Another issue is if you build a tool like this, you have to, I think, accept the fact that you're only going to get a 90% solution. Sometimes the advice is going to be a little bit wrong. You have a job that's doing something a little strange, and that in general this should be a red flag for having cancer or something like that. But in this case, whatever, your immune system is fighting it, or you're doing something weird, or you're bionic. So being able to tag false positives is another thing that we want to add quickly. Any other questions? You're saying the job inspection? So right now, bytecode modification and introspection happens at the point when a workflow zip file is uploaded to Azkaban. But there is no reason why we couldn't actually hook in at a lower layer, like a job submission time, and that way we would catch both things coming from Azkaban as well as coming from other workflow schedulers. They are able to submit, yeah, so you can run a job from the command line. Yeah. It would not, that is true. But in general, things that people are running from the command line in an ad hoc fashion, because of the way teams are organized, in a sense, that's not our problem. So we tend to focus on the things that are generating support tickets for us first. But also, people who are running workflows that have an SLA that they have to hit, anything that happens on the production clusters is a scheduled job that goes through Azkaban. So that was a way for us to sort of hit the high priority, use cases which cover probably 99% of the jobs that get submitted. You had another follow-up question. So we should quickly explain what support actually entails. Basically, the workflow manager needs to inject a couple properties into the job configuration, which just provide a link back to the Uzi project or the Azkaban project or stuff like that. And as long as this is like a unique key, a primary key that Dr. Elephant can sort and aggregate on, we're good. So the integration is like a fairly lightweight process. Are you up to date with the Uzi integration at this point? Oh.
We are waiting. I mean, there are a few users who are interested in Uzi. We are still working on to see who's going to implement, but it's in the roadmap. We don't have a definite date yet, but we'll have that soon.
And
Because it's a plugin model for any scheduler. That's how you see Airflow has a plugin for a Dr. Elephant. Similarly, it's easier to do for Uzi, but it's a work in progress.
And speaking of that, we should probably get that documented on the wiki. Like, here's the process for adding support to a new scheduler, like Pinball, for example. Any other questions? Yep. So these rules come with Dr. Elephant, and they're automatically applied to all of the jobs. And there's also, like I mentioned, the plugin API, so you can implement new rules on your own. But all the rules that we have are basically provided by people on the Hadoop team right now at LinkedIn, and we've seen like a couple of cases where some power users will suggest changes to rules, or will even sometimes submit pull requests to get those changes made. The rules for Spark were implemented by another team at LinkedIn, so that's sort of another example of another team using the plugin API and being able to extend Dr. Elephant with it. Yes? Okay, so this is a good question to ask. So the inspiration for so the motivation for Dr. Elephant was I wanted to stop spending time doing production reviews and watching people on my team, waste time, and watching people on my team waste the time of other people, doing these production reviews. The inspiration came from this book, the title of which I forget, written by Alex Holmes. It's one of the Hadoop trade paperbacks. And there's a chapter in that book on how to tune Hadoop jobs. And on one page, there is a flow chart, like a decision tree, basically, of, what is the value of this metric? If so, then you need to go and tune this, and here's the change that you need to make. And I had previously randomly sort of seen these textbooks that first-year medical students use, which have the same thing in them. There are flowcharts for diagnosing different diseases based on symptoms that you observe. Another thing is, like, if any of you have ever looked at like rule-based systems, things like Drools or Jenna or some of these expert systems that were really popular in the 1980s, you may be familiar with the idea that like just by sort of coding up a bunch of rules, you can get a computer to recombine them in interesting ways and come to pretty cool conclusions based on a set of input criteria. So it seemed like we had all of the basic pieces we needed to fit together. And we happened to have a really productive summer intern that year who we let loose on this, and 6 weeks later we had probably about 50% of what you see here. Not quite as many rules, but the basics of the system were there. Any other questions? Who's the what? Oh, so that would be Jay Krebs. So yeah, Jay, I guess, was a Harry Potter fan at that point, and then I believe he became a fan of Franz Kafka, and I'm not sure who he is reading right now, but I guess we'll have to wait for the next project to come out. Any other questions? Yep. Good question. So the question was, what are the most commonly violated rules? I'm going to pass this to Fangxi.
Yeah, so based on my experience, I think memory settings. So a lot of people are increasing memory, but they didn't really use that memory.
We should add that, like, memory is kind of one of the interesting settings, right? Because if you run out of memory, your job fails and you miss an SLA. So it is a form of insurance, right? You always have to provision enough for the maximum that you're going to need, only if you use it some of the time. So in a way, it's not surprising that that's the most frequently violated rule. And we've been doing some sort of separate work about doing a better job of tuning container sizes and responding to them more quickly. One of the core principles of Dr. Elephant up to this point has been that Dr. Elephant offers advice. It doesn't go and modify your job for you. Because I think with a system like that, you're going to make the wrong decision some percentage of the time, and you're going to get a lot more trouble for that than the 99% of the time when you make the right decision. So this gives us a way, right, of, you can take our advice or leave it, but do no harm. Exactly, the Hippocratic Oath.
So from this draw, actually, you can see the max request max required physical memory is like 800 megabytes, but this user actually requested 2 gigabytes container size, which means that it only used around 40% of the memory they requested. But why we flag it as green is because 2 gigabytes is our cluster default. So if our cluster default is now 2 gigabytes, this job, this heuristic will be flagged as like probably yellow or orange or red, because that we probably will suggest the user, in this case, it should be safe if you set your container memory to 1 gigabytes, and essentially you save 1 gigabyte memory. Sorry? But right now, I think, no, I don't think user will want that. Yeah, but this is cluster default, and we are thinking about like if we can like decrease it, but just we couldn't do that because it will break a lot of jobs. The max physical memory is get from job counters. Yes, so Hadoop will provide you a physical memory snapshot in these counters. This counter, in each task, it has a memory snapshot counters. No, yes. So there's so I think it has so for each snapshot for each task it has like 8 memory snapshot, I think, or 12. So basically we get the max. We use the max.